In this video, we're going to talk about homogeneous first-order linear systems with constant coefficients. So a reference for this is Boyce and DePrima, section 7.5. And this is about solving systems of differential equations. And I think the best way to explain the general method for doing this is to give a concrete example. And so I'm going to use this example of solving the equation x prime equals the matrix 1, 1, 4, 1 times x. So let's call this matrix A. Okay. So what we're doing is we're trying to find x, right? We're trying to find this vector. Remember, this vector is really just a shorthand. So this x of t consists of x1 of t and x2 of t, the components. So you have two different functions, and you have this equation, this matrix vector equation relating the two functions, x1 and x2. Okay, and the question is to find all the possible values, the possible functions x, which is the same as finding all possible x1 and x2. All right, and we know by the general theory that we should have two independent solutions. So we need two independent solutions. Once we have two independent solutions, then the general solution consists of linear combinations of those two independent solutions. Okay, that's just part of the general theory when you have a 2 by 2 matrix. So the idea is to try finding solutions, and this try will work. It turns out it works. Try finding solutions x of the form the book uses x equals c e to the rt, where this she, I think it's xi in Greek, I think, is a vector. Okay. So I think this is a bit hard to understand. I mean, it takes getting used to. Let's just write it in terms of the component functions. So in other words, so if this she is equal to c1, c2, then my x1 of t would just be c1 e to the rt, and x2 of t would be c2 e to the rt. So we're trying to find x1 and x2 of this form, okay, that satisfy this differential equation, this system of equations. Well, let's write out. So now what we're going to do is we're going to find the c1 and c2 and the r that make this matrix vector equation work. So what we have to do is we have to figure out the left side and we have to figure out the right side. Well, the left side is easy. So x prime is just the derivatives, right? It's just x1 prime, x2 prime. So that's equal to, by the chain rule, it's going to be rc1 e to the rt and rc2 e to the rt. Okay, so that's the left side. Now we have to figure out the right side and match. Well, we're going to figure out what the right side is, and then we're going to match the left side with the right side and see what happens. So this is going to be the matrix 1, 1, 4, 1 times c1 e to the rt, c2 e to the rt, right? Because that's my x1 and x2. So now I do the matrix multiplication. I get c1 e to the rt plus c2 e to the rt, and then 4c1 e to the rt plus c2 e to the rt, right? So the system of equations I'm given that I'm trying to solve is when both of these two are the same. So that's going to give me C1 e to the RT plus C2, right, so these are equal. Okay, so C1 e to the RT plus C2 e to the RT equals RC1 e to the RT. 4C1 e to the RT plus C2 e to the RT equals RC2 e to the RT. So I'm trying to find C1, C2, and R that make this equation true. Well, what's nice is that I can divide both sides by e to the RT for each of the equations. So this is going to tell me, this is equivalent to solving C1 plus C2 equals RC1, 4C1 plus C2 equals RC2. Wow, look, we just got a system of equations. And we're going to now subtract and get the variables over on one side. So we get C1 minus RC1. I'm going to factor out the C1. So I get C1 times, I can even write it like 1 minus R times C1 plus C2 equals 0. And 4C1 plus 1 minus R C2 equals 0. Right? That's just basic algebra. And now I'm going to rewrite this as a matrix times vector equation. I'm going to get 1 minus R, 1, 4, 1 minus R times the vector C1, C2 is the 0 vector. Does this look familiar? I hope it does from your linear algebra class. So let's think about what this matrix is. Remember that our original matrix was A, which is this, right? Now what we ended up getting is this. That is the matrix A minus Ri. This is exactly the sort of thing that you get when you're finding eigenvalues and eigenvectors. Okay, and then you have the C1, C2 equals the 0 vector, right? So remember, we're trying to find C1 and C2 that are not both 0. So we need a non-zero solution. If C1 and C2 are both 0, then we would just get x1 is 0, x2 is 0. So that would just be the 0. That would be x of t is the 0 function, right? Which is a solution, but we want other solutions. So we want a non-trivial solution to this matrix vector equation. We want C1 and C2 to not both be 0. And when does this system have a non-trivial solution? That happens precisely when the matrix A minus Ri is not invertible, right? And that happens if and only if the determinant of A minus Ri is 0. Okay. So they're all the same thing, mathematically equivalent. So let's calculate the determinant of this A minus Ri. So the determinant of A minus Ri, that's the characteristic polynomial of A, right? Okay, just to remind you. So we're calculating the characteristic polynomial of A, and we end up getting, okay, the determinant, so let's see, it's going to be r squared minus the trace. So we have a 2 by 2 matrix. So we add the diagonal entries, so we get 2 minus 2r, and then plus the determinant. So it's going to be 1 minus r squared minus 4. That's actually more complicated than it should be. Did I mess this up? Okay, no, I messed up. This is wrong. Let's just do the determinant like normal. Oh, I see. It's because I already calculated A minus Ri. Sorry. I was mixing this up with something else. There's a fast way of finding the characteristic polynomial, but let's just do it this way. So you just take the determinant, so it's 1 minus r squared minus 4 times 1. So this is going to be, so we set this equal to 0 to solve for r. And okay, we could move r to both sides and then take the square root of the equation. But I'm just going to expand it out. So it's, when you're calculating these characteristic polynomials, it helps to keep in mind that when you have 1 minus r in parentheses squared, it's the same as r minus 1 parentheses squared. So this is going to be r squared minus 2r plus 1 minus 4. That's minus 3 equals 0. So these are equivalent. And this is equivalent to r minus 3 times r plus 1 equals 0, and that's equivalent to r equals 3, or r equals negative 1. So what are my r's here? The r's are the eigenvalues, aren't they, of the matrix? That's what we just calculated. The eigenvalues, the roots of the characteristic polynomial. Okay, so now that we've done that, we have to go back and solve for C1, C2, because remember, we're not done. We're trying to find our x, and our x consists of, the components are C1 e to the RT and C2 e to the RT. Now, it's not true that any C1 and C2 will work, okay, because we need C1, C2 to satisfy this equation. So what is this vector C1, C2? That, in the linear algebra terminology, those are the eigenvectors, right? That's an eigenvector with eigenvalue r. So now we have to find the eigenvectors with eigenvalues 3 and negative 1. And now we do our linear algebra stuff. So for r equals 3, we have, we need to find a minus ri, so a minus 3i is going to be negative 2, 1, 4, negative 2, right? And we need to find an eigenvector. So we need to find a vector in the null space of this. Okay, so I see that this is a rank 1 matrix. Its null space is one-dimensional. So we need to solve negative 2, 1, 4, negative 2 times C1, C2 is the 0 vector, but I know that it's spanned by, this solution set is spanned by one independent vector. So I just need to find one vector in the null space. By the way, I'm trying to find one specific C1 and C2. So I can find that, okay, C1 equals 1, C2 equals 2 will work, right? When I take the dot product, I get 0 for the top and bottom. And so I found my possibility, my first possibility for x. Let's call it x with a superscript 1 in parentheses. That's going to be 1, 2 e to the RT, or e to the RT, 2 e to the RT. Okay? See, notice why I use the superscript, because I want to distinguish that from x sub 1, which is e to the RT. Okay, so now we do the other eigenvalue, negative 1. So we calculate a plus I, that's 2, 1, 4, 2. And again, we just need to find a vector that matrix times that vector is the 0 vector. And we can just take C1 to be negative 1, C2 to be 2. And so that's going to give me a second solution, x superscript 2, which is negative 1, 2, e to the RT, and that's just negative e to the RT, 2 e to the RT. Okay? So I know that my solution space is two-dimensional. I just need to check that I have independent solutions. So let's check that we have independent solutions. Actually, I think in general they will be independent solutions, but let's just run it through the Wronskian anyway. So this is the Wronskian where we have our two solutions, and it's the determinant e to the 3t, e to the minus t, 2e to the 3t, oh wait, this is negative, and then 2e to the minus t, right? Oh, I used r here. I should have used, I should have plugged in my, what r was. So 3t. Okay. And when you calculate the determinant, you get 2e to the 2t minus minus, right? So it's plus 2e to the 3t, 2t. So you get 4e to the 2t, which is non-zero. And so we see that these are independent solutions, and so we get the general solution is x of t equals constant. So this is a different c1, it's just a constant times x1 of t plus a constant times x superscript 2 of t. And I can write that as c1 times 1, 2 e to the 3t plus c2 times negative 1, 2 e to the minus t. And or I could write this out and write the component functions. x1 of t is c1 e to the 3t minus c2 e to the minus t. x2 of t equals 2c1 e to the 3t plus 2c2 e to the minus t. So each constant c1, c2 gives you this solution. Okay. So that's the solution to this system of differential equations. Let's try to summarize what we did. So we started out finding solutions of the form constant times e to the rt. And we saw that when we evaluated both sides and set them equal to each other, it ended up reducing to this linear algebra question. We ended up having to find the eigenvalues of the matrix A. And the C1, C2, that worked. So the eigenvalues give you the R's. The C1, C2s are given by the eigenvectors with eigenvalue R. Okay, that's what gave us our two solutions. And we checked that they're independent. And that gave us the general solution. And the general method is to do exactly the same thing. So if we have, in general, to solve x prime equals a times x, what we need to do is we need to find eigenvalues of A. Now suppose, so let's say A is an n by n matrix. And this is with constant coefficients, right? So we have a matrix with constant entries. So we find the eigenvalues of A. And suppose, so if A is an n by n matrix, suppose that there are n distinct eigenvalues. Well, we know that that means that the matrix is diagonalizable. And so let's call the distinct eigenvalues lambda 1 to lambda n. So we find corresponding eigenvectors v1 to vn. So V1 is an eigenvector with eigenvalue lambda 1, etc. Then, if you have x1, which is V1 e to the lambda 1t up to xn equals Vn e to the lambda nt, these turn out to be independent solutions. So we have n independent solutions. So the general solution is x, which is c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t plus dot 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 plus cn vn e to the lambda nt. That's the general solution. If your matrix A has n distinct eigenvalues, of course, your matrix A might not have n distinct eigenvalues, but if it does have n distinct eigenvalues, then this is the general solution. For the exact same reason as in the example we just did. Okay, because you can find the solutions and you can check with the Wronskian that they're independent, and so by the general theory, this is the general solution. Okay, so that's a good place to stop. So a reference again is to read section 7.5 of Boyce and de Prima, Homogeneous Linear Systems with Constant Coefficients, for more details. And then we'll continue talking about other examples and what happens with other possible eigenvalues.